Hello, kids. Welcome to video explanations of electrical circuit exercises with Sosa. So this is the example of the exercise we saw in last class, which is a Kirchhoff's law example and Kirchhoff's laws example. And I'm going to be going through it in detail and trying to solve it. My writing is going to be extremely funky. You try writing with a mouse. Let's make this viral. This would be cool, wouldn't it? Okay, let's begin. Okay, so this is the circuit that we're going to be analyzing, and basically there are certain elements that are given to us. We've got a couple of power supplies there, a 10 volt and a 20 volt power supply. We've got three resistors, R1, R2, and R3. R1 is 10 ohms, R2 is 20 ohms, R3 is 40 ohms. And we've got three currents that are identified there as I1, I2, and I3. And these currents have been established with a certain direction. Remember that we can establish these directions however we want. In the end, when we do the calculations are going to tell us if that is the correct direction or not. Okay, and the sign of the end result is going to tell us that. And also, there are certain references with regards to how the loops are being identified in this circuit. Also, that is completely arbitrary. We could have identified it, each of the loops going either counterclockwise or clockwise, and in the end the calculations are going to give us, according to the signs, what the correct direction is. So let's get to it. Let's start using Kirchhoff's laws to find the missing elements of this circuit, which is basically the three currents. So let's look at this circuit right now, and before we start to solve it, let's try to identify the nodes, loops, and meshes that we have in the circuit. Okay, so the circuit has two nodes. Okay, the nodes are identified as A and B. Okay, so we've got two nodes. These are A and B. And there's A right here, and there's B right here. Okay, and so these two nodes, those are junctions where current is going to be divided. Okay, that's how we defined a node. So how many loops do we have in the circuit? Okay, so loops, we have 3. And the loops are going to be these paths that are going to go around the circuit where current is going to flow. And remember that a loop is a closed path where current is going to flow, where we only go by a particular element in the circuit once. And so basically we have 3 loops. Loop number 1, which is here on the left-hand side. And there are 3 elements in loop 1, which is the 10-volt battery, R1 and R3. Then we've got loop number 2, which is the one that's here on the right-hand side. And if we go around loop number 2, we're going to find the 20-volt battery, the resistance R2 and resistance R3. And then we've got loop number 3. Now loop number 3 is the one that goes outside the circuit. Okay, it goes through the outer rim of the circuit. And in loop 3 we've got the 10-volt battery, R1, R2, the 20-volt battery, and those are the elements of loop 3. R3 isn't part of loop 3 because it's going on the outer edge of the circuit. Okay, now how many meshes do we have in the circuit? Okay, so remember that the difference between a mesh and a loop is that the mesh does not contain loops within it. Okay, so if we look at loop number 1, there isn't any other loop inside loop number 1. So loop number 1 is a mesh. If we look at loop number 2, there isn't another loop inside loop number 2. So loop number 2 is also a mesh. However, if we look at loop number 3, we have 2 loops within loop number 3, which is loop 1 and loop 2. Therefore, loop number 3 is not a mesh. Okay? Now, to finish up identifying the elements in this circuit, we're going to see how many active elements we have. And remember that an active element is an element that provides energy to the circuit. So these are batteries, power supplies, and so active elements, we've got 2. We've got V1, that's a 10-volt battery, and V2, which is a 20-volt battery. These are the active elements, V1 and V2. And what would be the passive elements in the circuit? The passive elements in the circuit are those that are going to absorb energy from the active elements throughout the circuit. And so the passive elements in this circuit would be, in this case, the resistors, okay? And we've got 3 resistors in the circuit, and these would be R1, R2, and R3. Okay, so I'm going to leave that in. That's Sarah asking me for pizza. And she is angry because I'm not giving her any pizza. I'm going to leave that in because I don't want to record this slide again. Okay? I hope this part is clear. And so now that we've identified the elements in the circuit, now we're going to see how we can use Kirchhoff's laws to find the variables that we want to know the values of in the circuit. And these are basically the currents. So the first law that we're going to apply is Kirchhoff's current law. And this is law number 1. And basically, Kirchhoff's current law says that current is the law of conservation of current. That means that in a node, all the currents that are coming in have to be equal to the currents coming out. So if we look at node A, we're going to look at node A. What are the currents that are going in to node A? We've got I1 and I2 going in. So the sum of these two are the currents that are going in. And then we've got the currents that are coming out. In this case, it's just one current. That's I3. Okay. Now, let's look at node B here on the bottom. In node B, we see that the current that is going in is I3. It's the only current that's going in. And the currents that are going out are I1 and I2. We know they're going out because the arrows are pointing outward of the node. So we've got I1 and I2. Okay. Correct that. Okay. And so we notice that actually these two equations are exactly the same, or they're equivalent. That means that, and that also proves the law of conservation of current. So all the currents that go into nodes go out of nodes, and these two equations represent this, and it's actually the same equation. We're going to leave that there because we're going to use this further on to find the values of I1, I2, and I3. Okay, so now we're going to be talking about Kirchhoff's voltage law, or KVL, which is basically the second law, right? And basically this law states that, or it's the law of conservation of energy, and it says that the voltage that is supplied across a loop has to be equal to the voltage drops across a loop. And so to do that, we're going to establish some references here in the loop. And so these references have to do with the polarity of the voltages in the loop. And so for power supplies, the smaller line is going to be the negative, and the larger line is going to be the positive. Same here, negative and positive. And for each of the components that we have here, we are going to include also reference voltages. How are we going to do that? We're going to do that with regards to how the current is entering and coming out of the element. So where the current is coming in, we're going to say that that's the positive side, and when it's coming out, we're going to say that's the negative side. And I'm going to call this voltage VR1. Over here, we're going to notice that for this resistor R3, the current that's going here is going in on this side, and it's going out on this side. And I'm going to call this voltage VR3. And over here on R2, we're noticing that the current is coming in on this side and it's coming out on this side. And so we're going to say this is VR2. These currents, I1, I2, and I3, they've been established in those directions. Those directions could be different. At the end of the day, the signs that we get from those currents are going to tell us if they were assigned correctly or if they go the other way around. So now if I go to node number 1, what I'm going to notice is the following. I'm going to follow the loop. And so the first thing I find here is V1, which is minus 10 volts. Why is it minus? Because the current in the loop that I'm analyzing here goes into the negative. And then we've got plus VR1. And then we come over here and we find plus VR3. Okay, that would be the equation for node number 1. And this has to be equal to 0 because the voltage supplies have to be equal to the voltage drop, so everything has to be balanced. And so we can rewrite this to say that VR1 plus VR3 is equal to 10. And the same law applies. The voltage supplies are equal to the voltage drops. And we can substitute the values of the voltages of the resistors using Ohm's law. So the voltage for resistor 1 is going to be R1 multiplied by I1. And the voltage for R3 is going to be R3 multiplied by I3. And this is still going to be equal to 10. And we know that R1 is 10 ohms, so this is going to be 10 I1. And we also know that R3 is 40 ohms, so this is going to be 40 I3. And this is going to be equal to 10. And so just to simplify this a bit, we can divide by 10 the whole equation. And what I'm going to get is an equation that says that I1 plus 4 times I3 equals 1. Okay, and that would be the equation for loop number 1. And so now we're going to do the same for loop number 2. And what we're going to see in loop number 2 is that we're going to do the same thing. We're going to go through the loop. So the first thing we find here is minus 20, which is the power supply. So we're going to write down a minus 20. The next element we find is VR2. goes through the positive and out of the negative, so this would be plus VR2. And then we continue and we find plus VR3 because it's going through the plus and out of the negative. So it's plus VR3. And this has to be equal to 0 according to Kirchhoff's voltage law. Okay? And so we can rewrite this and say that VR2 plus VR3 equals 20. Now VR2 and VR3 are the voltages in resistors 2 and 3, and using Ohm's law we know that the voltage in resistor 2 is R2 times I2. The voltage in R3 is R3 times I3, and this is going to be equal to 20. If we substitute R2 and R3, so R2 is 20 ohms, so 20 I2, R3 is 40 plus 40 I3 is equal to 20. And just to simplify this a bit more, we can divide everything by 20 and we're going to get I2 plus 2 times I3 is equal to 1. And that would be the equation for loop number 2. And so now for the last loop, which would be loop 3, we're going to do exactly the same thing. We're going to go through the loop. And so for loop 3, we are going to look at the voltages. And I'm going to start over here. I've got minus 10 volts because I'm following the path and goes through the negative. Then I've got VR1, it goes in through the positive, plus VR1. Then I encounter VR2, but notice that if I'm following the path, it goes through the negative VR2, and this is because the sign of or the direction of this I2 was going from here to here, and now I'm going the opposite way, so this would be minus VR2. And lastly, I find the 20 volt supply that goes through the positive, and so this is going to be plus 20. And this has to be equal to 0, according to Kirchhoff's voltage law. And so I can simplify this. So 10 minus 10 plus 20 is 10. So this would be the same as having 10 plus VR1 minus VR2 equals 0. And I can send this 10 to the other side, and this would be VR1 minus VR2 equals minus 10. And I know that the voltages in VR1 and VR2 are dependent on the currents and the resistances. So the voltage on R1 is going to be R1 times I1. The voltage in R2 is going to be R2 times I2. This is going to be equal to 10. And then 0 to minus 10. Let's not forget the sign. And we can substitute the values of R1 and R2, which are 10 ohms, I1, minus, in the case of R2, it's 20 ohms. And this is going to be equal to minus 10. I can divide everything by 10, and this is going to give me I1 minus 2 times I2 equals 1. And this same minus 1, I'm sorry, minus 1. And this is equivalent to having 2I2 minus I1 equals 1. Multiplying everything by minus 1. The two equations would be equivalent, and so this would be the equations for loop number 3. Okay, so now after applying Kirchhoff's current law and Kirchhoff's voltage law, we've gotten 5 equations. However, we've got 3 variables, which is I1, I2, and I3. So really, we just need 3 equations that relate any of these variables in any sort of way. So actually, some of these equations are redundant. Okay, and let's look at that. So for example, if I take these 2 equations, we had already mentioned that both of the equations are the same. Okay, so I can just use one of them. Okay, so I'm going to call this equation, I'm going to put it in red. I'm going to call this equation 1, just for the purpose of the analysis. And then from these 3, I'm actually just going to stay with these 2 up top. I'm going to not use this one. I can use any of the ones I want. So I'm going to call this one equation 2. And I'm going to call this one equation 3. And so I am going to play around here with these equations. So I'm going to substitute equation 1 into equations 2 and 3 and see what happens. And so we've got 3 equations. We're left with 3 equations. We've got 3 variables, and let's play around with these with some linear algebra here. And so what we're going to be doing is that I'm going to substitute equation 1 in equations 2 and 3. So if I do that, I'm going to get from equation 2, I'm going to get I1 plus 4 times I1 plus I2, which is I3. This is from equations 1 and 2, and this would be equal to 1. This is taking equation 1 with equation 2. We get this. Okay, simplifying this a bit, what we're going to have is the following. We're going to have I1 plus 4I1. This is going to be equal to 5 I1 plus 4 times I2 equals 1. Okay, and this is a new equation that we're going to be using. Okay, Now I'm going to take equation 1 and substitute it in equation 3. What I'm going to do there is that we're going to have I2 plus 2 times I3, and we know that I3 is I1 plus I2, and this is going to be equal to 1 also. Now this is taking equation 3 and equation 1 and joining these together, we get this. And so substituting here, we're going to have, I'm going to reorder this, we're going to have 2 times I1 and 2 times I2 plus I2 is going to be plus 3 times I2 equals 1. And this is going to be a new set of equations. I'm going to call these, I'm going to call this one equation 4. And I'm going to call this one equation 5. Okay, so now we've got these two equations. The rest of what I'm going to be doing right now, this is just maths. I'm just going to be practicing some math here for you guys. And so basically what we've got here is these two equations. I'm going to be multiplying one of them by 3. I'm going to be multiplying the other one by -4. And what I'm doing here is just a series of manipulations to solve the equation systems. You can solve them however you want. I'm just playing around here. So this is going to be 15 I1 plus 12 I2 equals 3. This is me just multiplying the first one by 3. The second one is going to be minus 8 I1 minus 12 I2 equals -4. And then I add these up, and the first one is going to give me 7 I1. And these two are going to cancel themselves out. And this is going to be equal to -1. And so that means that I1 is going to be equal to -1 divided by 7. And if we do this in the calculator, this is going to be -0.142. I'm going to be using just I'm going to be using 3 decimals there. Okay. So that's I1. Now I can grab I1 and I can substitute it in the first equation to get I2. So if I substitute it here, I'm going to get 5 times 0, and it's important for it to be negative, 0.142 plus 4 times I2 equals 1. And this is going to give me negative 0.71. plus 4I2 equals 1. And so this looks like a T, a little bit better. And so this gives us then that 4 times I2 equals 1.71. And so this means that I2 would be equal to 1.71 divided by 4. And this would mean that 1.71 divided by 4, let's do that calculation quickly. 1.71 divided by 4, that's 0.4275. So I'm just going to use 3 decimals again. So that's 0.427. And lastly, let's remember that we had equation 1. And equation 1 said that I3 was equal to I1 plus I2. And so this means that I3 is the sum of minus 0.142. I'm going to erase that. No, I'm not. The last time I tried to erase something with the eraser icon, it erased the whole slide and I got really mad because I had to do it again, and I've been doing it for about 2 hours. So no, I will not do that. You understand that this is a 1. And if you don't, then, well, that's your problem, not mine. So it's going to be minus 0.142 plus I2, which is 0.427, and that's going to give us an I3 that is equal to minus 1.42 plus 0.427. So let me see that again. Okay, 0.427 minus 0.4142. Okay, and that gives us 0.285. Again, I'm just using 3 decimals. 0.285. Okay, and let us not forget that these are amps. That's the unit that we've got there. Amps, amps, and amps. And these would be the 3 values that we have been looking for. Okay, so it's I1 equals 0.142 amps. It is I2 that equals 0.427 amps. And it's I3 that equals 0.285 amps. These were the 3 values that we were looking for. Okay. And so just to recap, we've got the 3 values of current that we've just found. So I1 equals minus 0.142 for 2 amps. I2 is going to equal 0.427 amps, 0.427 amps. And lastly, I3 is going to equal 0.285 amps, 0.285 amps. Okay. Oh, I could use the eraser there. Last time I used the eraser, it erased everything, and I got real mad. So it didn't happen here. So those are the three currents that are here in the circuit. Okay, and so just so we can practice Ohm's law. Remember Ohm. That's Ohm's law. Let's find the voltages in the resistors. So the voltage in R1 is going to be the resistance in R1 multiplied by the current I1, and this means that it's 10 multiplied by, whoops, I'm going to be using the eraser now. There we go, we can erase. I should have used that before. Minus 0.142. And so this means that the voltage in R1 is going to be 1.42 volts. And actually, we got to be careful because this is negative. And we have to remember that it is a negative voltage, and we're going to comment on that in a bit. And then the voltage in R2 is going to be equal to R2 multiplied by I2, and this is going to be equal to the resistance in R2 is 20 ohms. Multiplied by 0.427, this one is positive. And that means that the voltage in resistor 2 is 20 times 0.427. And that gives us 8.54 volts. And lastly, the voltage in R3 is going to be R3 multiplied by I3. And so this is going to be 40 ohms. Multiplied by 0.285. And so this is going to be, let's see, 40 multiplied by 0.285. And that's going to be 11.4 volts. Okay. Notice that none of the voltages can be larger than the largest voltage, which in this case is 20 volts. And also, if you notice, let's talk a little bit about the signs. So what's happening here is the following. I1 is negative. The only thing that means is that the original direction that we identified I1 as this way, the only thing it means is that really I1 is going this way. Okay? So the sign indicates that it means it's just the other way around. And in this case, the voltage in R1 is also negative. That only means that since the current is going this way, then actually the voltage in R1 has this polarity, okay? Which is the opposite polarity as the one we had identified, okay? And so this way now we have all of the values of the elements in the circuit, okay? And so I hope you understood, and this explanation was a bit more detailed than the one we saw in class, and you've got the video here to be able to review it whenever you want, okay, with bloopers and everything, okay? I hope you enjoy it. Let's make it viral. Let's make my classes viral. That would be fun, and I would be famous, and I'd love to be famous. Follow me at my Twitter at Jorge Sosa L. It's fun, it's entertaining, and maybe you'll learn something. So, see you guys. Cheers. Bye-bye. And so ends another exciting episode of Solving Electrical Circuits with Sosa, Kirchhoff's laws example. See you. Bye.